We put up some of the quiz stats here. The mean was about 75, and I must tell you that that's very impressive. I guess MIT undergrads never cease to amaze me. And this was not an easy quiz. This was a relatively hard quiz, and that average implies that you guys did well on a relatively hard quiz. Good. Okay, let's get back to a final lecture on amplifiers and small signal circuits. And as always, let me start with a review. So very quickly, we came up with a notation to represent small signals. And our notation looked like this. Our total variable was small and capital. And this was a DC bias. And this was a small signal. Okay, this is also called the operating point. And the small signal is also called the incremental signal. In general, if you have some function, some variable of interest in the circuit, say a total variable V out, let's say it relates to some input variable as f of Vi. So mathematically, we can find out V out by simply finding the slope of this function at the operating point and then multiplying it by the incremental change in the input. Good standard math. So we would do the slope of this function and evaluate it at the operating point. So this would give us the slope of the function and multiply that by small vi, which is incremental change. So this is standard math. So what this will tell you that given a small change in vi, this function gives you, this expression gives you the small change in v out. And in lecture, we've pretty much used this method so far, use the math to get to where you want it to be. And then the way we provided biasing and so on was for our amplifier in particular, we had a bias voltage, some small signal value, Vs, and this was an output which was also given to be some output operating point plus a small change, which was the change in the output voltage. So what we've done here is mathematically computed small v out. And what I'm showing you here is to get the same effect in a circuit is you build your circuit and replace what used to be a total variable with a DC bias plus a small change. And then you'll get your output here. And this output will relate to this input using this expression. So to continue on with the this is more review. To continue on with the math view. So for our amplifier, V naught was given to be Vs minus K divided by 2, Vi minus Vt whole squared RL. Okay? So we this was the output versus input relationship for the amplifier. And mathematically, I could get the small change in the output V0 by simply differentiating this function with respect to VI, evaluating that function at capital VI and multiplying by the small change in the input. Okay? And the resulting expression that we got for small VO okay, was simply minus K. Okay, this was our DC value, and RL times small VI. Okay, so we derived all of this the last time, so there's nothing new so far. So my small signal output was some function given by K VI minus VT RL times small VI, and notice that this is how VI relates to VO, and this is a constant with respect to VI. V capital I is a DC bias, so this is a constant. So therefore, this is the linear relationship that we had set out to get. This term here, for reasons you will see today, this term here, K VI minus VT, is called GM, okay, transconductance. We will look at it in more detail a little later. Even more review. So I can draw the transfer function and plot VO versus VI. Another way to graphically view what's going on is by plotting the load line curve for this circuit. So this is VI. And I said we draw that by first plotting the so these were our MOSFET curves, and we know that at some point the MOSFET gets into saturation. So this curve was IDS equals K by 2 V naught squared. And to the right side of the curve, the MOSFET is in saturation. And we said we're going to adhere to the saturation discipline and operate in this regime. Okay, when the MOSFET gets into this region, it is in its triode region. And then we could draw the load line here. Okay, the load line codified the following relationship. IDS Vs divided by RL minus V naught divided by RL. Okay, this was a load line. Okay, so I superimpose a load line on the device characteristics, and I'm going to show you a little demonstration based on that at this point. So these curves were drawn for increasing values of VI, and if I choose some point, some operating point here, then this point would correspond to some bias. This bias point would correspond to some input voltage VI, a corresponding output bias VO, and a corresponding current IDS. So IDS, capitals, VO, capitals, VI, capitals, represent the operating point values for our little circuit. Okay, so far there's nothing new. Okay, so one thing we stopped the last time by pointing out that the gain of our amplifier, okay, the gain of our amplifier, this is the gain, minus K VI minus VT RL, that's the gain A of the amplifier. That gain related to VI. Okay, a gain was proportional to VI minus VT. So therefore, if I increased VI, I would get more gain. So the question is, how do we choose a bias point? And in our particular example, let's say we are free to play around with VI. Okay? So you play around with VI, and I can choose various bias points. So where do you set the bias point? Okay, what are the what are the various characteristics of the circuit that relate to my bias point? Well, first, of course, is gain. Okay, the gain depends on how I choose VI. Okay, I'll show you that in a moment. The second important thing, in other words, if I choose a bias point that is a small VI, then my gain is going to be smaller. If I choose a bias point that's at a much higher value of VI, I get a bigger gain. The second important consideration is operating range. Notice that if I choose a bias point here, okay, then as the input changes, okay, notice VI in this graph, VI goes up or down, and I would be traversing and following different lines here in my MOSFET characteristic. And as VI increases, the operating point would come up here and so on. So if above this operating point, I varied my input voltage VI, then, so let's say, about this operating point, if my input VI, my small signal VI, varied about a small range, then correspondingly, the output value would vary about this part of my load line. Okay? So notice now that the operating range, how far can VI vary before the MOSFET goes out of its saturation discipline? Well, on the low side, my VI can come down till here, and we looked at the operating ranges for an amplifier, and I can come all the way down to VT. Okay, at that point, the output will come here. Similarly, at the high end, VI could get up to a high value, and we computed that value in the last lecture, and the corresponding value at the input would be here. So in some sense, I can traverse all the way from here to here and have my MOSFET remain in saturation. Remember, we're not talking about linearity right now, just about the valid operating range based on my definition, which is that the MOSFET should stay in saturation. So if I choose my operating point here, then I get this range here. And on the other hand, if I choose my operating point to be here, okay, for negative excursions of the input signal, I have a very small amount before I hit cutoff. So if I choose my operating point here, then for negative traversals of VI about the operating point, I very quickly hit cutoff. Okay, so if I want symmetric swings, then this is the best that I can do in terms of the valid input operating range, if I want symmetric swings, given that this is my bias point. On the other hand, if I choose my bias point somewhere here, or very carefully choose my bias point, then my input can vary over a much wider region and still get symmetric swings. And so therefore, the choice of bias point also influences the maximum swing range of my input signal. Okay? I shouldn't call this operating range. I should call it input swing range. Okay, we defined the valid input operating range as the range for which the amplifier satisfied the saturation discipline. Okay, so the two key issues, the gain and the input swing. All right, so let me show you a quick demo and try to point out on a graph some of the characteristics that relate to the matter we've been talking about so far. Okay, so what I show here is these curves for the MOSFET. This is V0, and this is IDS. Okay, this is the 0 point. This line up here, ignore this line down here. This line up here corresponds to the output voltage, VO. Okay, what I'm going to do now is, through some careful circuit hacking, I'm going to show you a load line and show you the bias point and show you how the bias point can be moved up and down by changing the input voltage, which changes the corresponding output voltage. It's hardly visible out there. Is it there? Okay. It's not very clear, but as I notice that as I increase my input, I'm increasing my input, my output keeps coming down. And I hope your eyesight's better than mine, because I don't see a dot out there. I'm amazed. This is the first time this has happened to me. Oh, that's okay. That's okay. All right. So as you can see, as I change the input value, the output operating point changes, and the dot out there articulates the load line. Okay? I guess I have to believe that there is a dot out there. Okay. So next what I'll do is show you some more fun stuff. What I'll do is instead of having just a dot by having a DC voltage, let me apply an input sinusoid. Okay? So if I apply an input sinusoid at some bias, then I should see an articulation of the corresponding region of the load line corresponding to the input. So as you can see here, so now the bottom line here is my input, and this is my output. And notice that this is the region of the load line articulated when the input is of this, this magnitude. Okay? Now, let's have some fun. As I increase my input, you can see that a larger portion of the load line is articulated, right? There you go. And as I decrease my input, a smaller region of the load line is articulated. Okay, let's leave it here for a moment. And what I'll do next is, this is the region here that we're looking at. Let me increase the bias. So if I increase the bias, if I increase VI, what do you think should happen to this line here? Well, if I increase the bias, the line should go up, right? Because remember the dot is in the middle of this thing here. If I increase the bias, this should move up here. Okay, so one is that line moves up. Do you expect anything else to happen to that line? Pardon? It increases, exactly. So if I increase the bias point to here, then this must also increase because my gain is increased. Okay, let me do that. So let me increase the input bias. You indeed notice that the region of the load line articulated is larger now. Let me decrease the bias, and notice that because the gain is smaller, the little segment shown is also smaller. Okay? So I've shown you two things so far. One is that as I increase my bias, the line indeed rises up, corresponding to a higher value for the operating point. And second, the input operating point. And the second is that I get a larger swing in the output as I increase the bias. Okay? Just to show that for those like me who were visually challenged in terms of viewing that little dot out there, let me play some, get some audio so you can actually hear the sinusoidal tone. It's a bit annoying. So as I reduce the bias, the gain is decreased. As I increase the bias, okay, as I increase the bias, you can see that the gain is increased and the tone is louder. Okay? Let's have some more fun, and let's play some music now. And what I'm going to show you with the music is the reason I play the music is not just for fun. Well, it's 85% fun and 50% learning. So let me turn it on for a second. So what I'd like to do is, so as we play the music, the reason I'm playing the music for that 15% is so you can listen to distortion. Okay? I want you to listen to the distortion. That is, when the articulation is here, you aren't going to get much distortion. Okay? But as I get into cutoff, you should be hearing a bunch of distortion. Similarly, as you get into the triode region, you should also be getting distortion because the amplification from being somewhat nonlinear here becomes highly nonlinear at those 2 points. Okay, so let's just play the signal. So volume increases by, or rather the amplitude increases by increasing the bias. Okay, now you should hear the volume go down and distortion. So notice now that the bias is way down here, so the gain is very low, and plus this is distortion because of cutoff. Now what I'll do is blast it up here, and you'll see that the volume has gone up, but then you see distortion again. And let's see if we can stand the volume here. Even the CD doesn't like that. Okay. So notice that as I went up here, the volume kept increasing. The volume kept increasing because the gain kept increasing. But as I got into the triode region, I began to lose my gain because, remember, the amplifier doesn't have gain in the triode region, and the MOSFET in its triode region, and we also get a bunch of distortion out there. Okay? So finally, it turns out that as people were building amplifiers in the, I think this was in the mid to late 50s and 60s and so on, they said, man, the electrical engineers ain't going to get their thing right. So they invented a new kind of music, which was much more tolerant to distortion. And I'll play that music for you. It's called hard rock. I challenge you to tell me it's distorting. Sounds good to me. Okay. All right, that'll do. Thank you. So I hope there are no, hard rock musicians in here. Someone beat me up after lecture or something. Okay. All right. So believe it or not, most of that was review. Okay, there's nothing new today besides some fun and games and so on. So I'll give you a breather for 5 seconds before jumping into something even more fun. So okay. So I want you to look at this, the middle board here. And as I told you in the beginning of 6002, that engineering is about building useful systems. Okay, engineering is not about showing off with math or saying, man, I'm really cool in math and stuff. Engineering is about building useful systems, and you want to find the simplest, easiest, cheapest way to get there. Okay, unlike deep areas of math and theory and so on, the beauty is in the simplicity. Okay, so the aesthetics are in how simple can we make things and still get to where we want to be. So all through the course, what you will be seeing happening again and again and again is whenever things begin to get too grovelly in terms of math, we'll step back and say, whoops, we're engineers, remember? Let's find a much simpler way to do it and use intuition. Okay, so time and time and time again, I'm going to take you down a simpler path where you can solve things by inspection by pure intuition. Okay, most circuit designers do that. So let's take a look at this. I don't like this nasty, differentiation here. When that's getting into late high school calculus and so on, and let's avoid the math. Okay, and let's see if we can get something find some way of doing it that's even much more simple. And that's what I'll do next, and show you what is called the small signal circuit view. Okay, a purely circuit way of developing the small signal model. So let me just start by drawing the large signal equivalent circuit for you. I'll draw it here for reasons that will be obvious at the end of the class. All right. So this is the large signal. This is the large signal equivalent circuit model for our MOSFET amplifier. Okay, VS, and here's my current source. IDS relates to the square of VI minus VT. Okay, so stare at that for a second, and that's a nonlinear circuit because IDS relates to the square of VI minus VT. So let me start by making the following claim. Okay, let me shoot from the hip here and make the following grand claim. And then I'll show you how I can prove that claim. The grand claim I'm about to make says the following. So a bunch of little devices here. It's a nonlinear circuit. Suppose, okay, just suppose for a moment, okay, do a Gedanken experiment. Suppose I replace each of my elements here, circuit elements here, with its linearized element equivalent. In other words, so here's a VS source. Here's a current, dependent current source. Let me replace them with their linear equivalent circuit models. In other words, with their small signal, with their corresponding small signal element models. Okay, and I'll show you what those are in a second. The resistor has a corresponding small signal element. The dependent current source has a corresponding small signal behavioral element model. And what I'm going to do is keep the same circuit. Okay, keep the same circuit connections. And simply pull out the large signal model for the element and replace it with a small signal element model. Okay, and by the nature, the small signal models are all going to be linear. So what I'm going to be left with is a linear circuit with simple linear circuit elements in there. And then once I have a linear circuit, I should be able to analyze that linear circuit using, methods 1, 2, and 3, superposition, Thevenin, node method, and so on. And certainly the intuitive methods like superposition and Thevenin, which make life a lot easier for me with linear models, and thereby get the function that I'm looking for very quickly. Okay, so again, my claim is that I can replace each of these large signal models by just small signal equivalents, and then just analyze the resultant circuit. Okay, and I claim that I should be able to get the same answer. Okay, that's a claim. All right, so what I'll do is give you an informal proof. Give you an informal proof for why I can do that. And I also ask you to refer to section 8.2.1 of the course notes to see, to go through the foundations of the small circuit model in more detail. Okay, the intuition is that, remember KVL and KCL. I can write down KVL and KCL for every loop in that circuit and every node in that circuit. So if I do KVL and KCL, I will end up with something like this. For the input loop, I get VI something or the other, applying KVL. For the output loop, I get V out something or the other. And then applying KCL, I get some other equation in IDS. Okay, so here are my KVL and KCL equations for that circuit. Now, KVL and KCL are simply a different representation of the circuit, because within those KVL and KCL is encoded the topology of the circuit. Remember, each KVL equation represents a loop, and each KCL equation represents how nodes are connected together. So the KVL and KCL equations encode within them the topology of my circuit. Okay, so what I do next is say I replace each of these with the bias plus the small signal. So I get the bias plus the small signal, and keep the equations the same. Okay, all I've done is, in my big Mongo set of KVL, KCL equations, I've simply replaced the total variable with the large signal variable and the small signal quantity. Then comes the key trick. Okay, the key trick is that because the bias point variables, okay, they are a valid solution to the circuit. Okay, the circuit is in this quiescent state, and those are a valid solution to the circuit. So therefore, I can cancel them out. Okay, so the VI, the large signal values, can be canceled out leaving just the small signal variables in there. So from the KVL, KCL equations, I can cancel out the large signal values, the DC bias points, because they satisfy the KVL and KCL themselves. In other words, I could have written VI plus V out, and so on. Okay, so since they're satisfied, I just strike out the large signal variables from both sides of each of these equations. So what's left is the same KVL, KCL equations, but with small variables in place of the big variables. Okay, what that should tell you, this informal proof should tell you then that the small signal variables, okay, should then satisfy the same form of the KVL, KCL equations that the total variables satisfied. Okay? And because these equations, the KVL, KCL equations, are a reflection of the topology of the circuit, what that says is that the small signal variables must also satisfy KVL and KCL. And since these arrive from the small signal elements, that says that I can replace the big elements with the small elements, and KVL and KCL will hold for the resulting circuit. Okay, this is a very quick breeze through an informal proof to show that I can replace the big elements with the corresponding little element models, and then simply apply linear techniques. Okay? Refer to section 8.2.1 for more foundations and more discussion about the foundations for why we can do this. So that brings up the small So the circuit method for small signal analysis has 3 steps. The first step is find first you analyze your large signal circuit and find the operating point. Okay, you have to do this because remember the small signal models depend on the operating point values. Remember, the gain of our amplifier depended on the bias point. So second step is develop small signal models Second step is take each of the elements in your circuit, okay, and find their equivalent small circuit model for each of the elements. Third step is replace Third step is simply take the large elements and replace them with their small signal equivalent models. Then analyze resulting circuit. And that circuit will be a linear circuit. Okay, so let's do an example. And I'll just use the amplifier as an example of this method and convince you that you're going to get the same expression at the end, but just so simply without even the smallest amount of grubby math. So 3 steps. And the first step is find the operating point using the large signal model. And let me just do that here. So I get my V out being equal to, we've already done that before. Okay, let me just write down that out here. Don't worry about copying that down. It's on the last page of your notes. So the first step of the method simply applies the large signal model and finds out the behavior of that circuit to find out what the bias point values are. Okay, the second step is to develop the small signal model of my elements. So how do I go about developing the small signal models of elements? So let's start with the MOSFET. The large signal model for the MOSFET looks like this. So here's my VGS. This is my gate. This is my drain. This is my source. And I know my IDS to be. So this is a large signal model for the MOSFET. Again, in saturation. Okay? I'm talking about all of these models are under the saturation discipline. So VGS relates to IDS in the following way for the MOSFET. That's IDS, is K by 2, and that's my square law relationship. So what's a corresponding small signal model? So I go ahead and start with this. The corresponding small signal model simply says that IDS relates to VGS in the following way. So all I have to do is find a small signal equivalent where I need to find out, given a small change in the input VGS, what is a small change in the IDS? Okay? So I can apply my standard trick to a much simpler expression here, which is IDS is simply I differentiate this function with respect to VGS. So I don't completely eliminate the math here, but it's a much simpler problem here. So at VGS equals the bias at the bias point times small VGS. Okay, so I can find the small change in IDS corresponding to a small change in the input using this expression. That gives me IDS is simply K times VGS minus VT VGS. Okay? I call this GM. I'll tell you why in a second. So what does this expression say? This expression says that if I have a small change in VGS, then this will be my small change in IDS. Notice that the resulting small signal model is also a dependent current source. It's a voltage-controlled dependent current source. Okay? So the output is a current, and it's a dependent current source, and it depends on the input voltage. The good news is that notice that this expression here, GM, is a constant, okay, related to the bias point values. So therefore, notice that the small signal model for the MOSFET in saturation, not surprisingly, is a linear voltage-controlled current source, okay, according to the following expression. So IDS equals GM VGS. GM is a representation for KVGS minus VT, and it's called a transconductance. It's called a transconductance because it is, in some sense, it reflects the conductance properties of this based on the input. So it's a transconductance. Okay, so this value is called VGS. Okay, so therefore I can build the small signal model as follows. VGS is a voltage-controlled current source, and IDS is simply GM VGS. Okay, so this is my gate, drain, source. So that's the small signal model for my MOSFET. So as the next step, let me, what are the other elements in my circuit? Let's see, I have a voltage source and I have a resistor. So let me find out the corresponding, this is page 7, the small signal model for a DC supply VS. Now, I'll do it mathematically for you, but oftentimes it's always good to do a sanity check using intuition. So let me ask you, for the large signal model for a DC supply looks like this. The element law for a voltage source is Vs equals some capital Vs. Okay, it's a constant voltage. So what do you expect to be the small signal model for a voltage source? In other words, for a small change, suppose I have a small change in the current. Okay? By how much should the output Vs change? It shouldn't change. It's a voltage source. So what's the intuition tell you is a small signal model for a voltage source? A short. So the key here is that a voltage source behaves like a short circuit for small perturbations. In other words, if I change the current flowing through it by a small amount somehow, the output is still going to be held at Vs. Okay, so in other words, small signals are simply going to scoot through this voltage source without having any impact whatsoever on the voltage. Or mathematically, I can also do small Vs is del by del Is of Vs evaluated at Is equals some capital Is times small is, and therefore Vs equals 0. So what that means is that the small signal model for my voltage source is simply a short circuit. So in a small circuit, voltage sources appear like a short circuit. Finally, I have a resistor. My resistor R, let me find out its corresponding small signal model. So the large signal model looks like this, R, VR, IR. Okay, and I know that VR is simply R, IR. And to find the small signal equivalent, I do del of R, IR divided by del IR for IR calculated at some constant value times small IR. Okay, so what I'm looking to do is to find out what is the change in the voltage across R for a small perturbation in the current. Okay, again, let me exhort you to rely on intuition to at least sanity check your answers. So what do you think? What do you think this should look like? If it's a resistor and I have a small change in the current, okay, by what do you expect the voltage to change? So think about, for the next 5 seconds, what the model, for the small signal model for this should look like, and then I'll go ahead and write down the answer. Okay, so differentiating, I simply get R, IR. In other words, for a resistor, the small signal model is the resistor itself. So what I've done so far, let me just take you through where we are right now, give you the big picture here. So I began by suggesting that I was looking to find an even simpler way to do small signal analysis. Okay, I gave you an informal proof to show that if I had small signal element models for all my elements, I could simply replace them in the circuit and then do a corresponding linear circuit analysis phase to get the result I'm looking for. So there are 3 steps to the method. And as a first step, we began by finding small signal models for each of our elements. For the nonlinear MOSFET, the small signal model was a linear dependent current source. For a voltage source, the corresponding small signal model was a short circuit. Okay, and that makes sense intuitively. If I change the current through a voltage source by a small amount, by how much does the voltage change? It's a voltage source, silly. The voltage doesn't change. So the small signal the small change in the voltage is 0. And that's the same thing as a short circuit. For a resistor, by how much does the voltage change if I change the current by a small amount? Well, it'll change by R times the current change. Okay? And that's the property of a resistor, R. So as a final step, what I'd like to do is on page 8, I'd like to very quickly draw for you the small signal circuit and then analyze it. So this is the large signal circuit. That's a large signal circuit. And let me draw the small signal circuit. And the method says simply pluck out, gouge out each of these elements. Okay? And simply replace each of these nasty nonlinear elements with the corresponding small signal linear equivalents. So let's do that. So for the input, remember, for the input, you replace the input with its small signal voltage because I'm telling you that it's sourcing a small change in VI. So that's VI. And then I replace a short for VF. Okay. I replace an R for RL because it's an RL itself for the small signal model. And then for the dependent source, I claimed, we discovered that the dependent source was a linear dependent source given where I, small IDS, was given by GMVI. Okay? And remember, this was my small VO. So here you go. So I have a small signal circuit here where I've simply created that by replacing each of the big elements by little rinky-dink elements. Now, these are all linear elements, so I can do a really simple linear analysis. So what method shall we use? Well, this is so simple, I'll just go ahead and use the node method. So applying the node method at the node with voltage V0, what I'll do is the current going up, V0 divided by RL, equals the current going down, IDS. Okay? And so the current going up is V0 divided by RL, and the current going down is I should have done this. The total current going out is 0, so the sum of these two is 0. That's my good old node method here. And I know that IDS is simply GMVI equals 0. Okay? So right there, I have the relationship between V0 and VI. So V0 is simply minus GMVI RL. And remember, GM was simply K VI minus VT. We are done. Okay? So what have we here? I created a linear circuit which simply comprised small signal models for each of my big elements. And then I simply did a straightforward linear analysis using any one of the linear techniques I knew about. This is simple enough, so I applied the node method. And I got the equation at this node, simplified it, and I directly got the answer. So in 1 or 2 steps, I directly gave you the output as a function of the input. Okay? It can't get any simpler. Thank you.